All right, first problem on the test 2 review problems. We want to draw a complete and accurate free body diagram of this beam with the distributed loads shown. So we've got we got distributed loads, a triangular distributed load and a constant distributed load. And then calculate the reactions at pin A and roller B. Oh, I got these mixed up. So this should actually be roller A. So pin B and roller A. So that's what we're looking for. So let's, what I did is I started by sketching out the beam here. This is a free body diagram. And a roller can only have a single reaction force. So pushing up, this is the direction, again, opposing motion, potential motion of that component. So we'll label that A. And then over here at the pin end, we've got two potential reaction forces, By and Bx. So this would be the correct thing to draw to pin two reaction forces. All right. So now what I'm going to do is I'm going to take these distributed loads, and I can't just put forces on here. I've got to take the distributed loads and convert them into point forces acting through the centroid of a cross section. So let's see, convert distributed loads to concentrated loads through centroid of the area. So let's see, I'm going to draw over here. I'm just going to draw two shapes. I'm going to draw a triangle and I'm going to draw a rectangle. I'm going to label where the centroid is. Again, this is in your textbook. It's also in the slides that we covered in class. Got a rectangle. And let's just call this, let's call this the base. And the centroid of a triangle is base over 3. So I'm going to put another, let's use another color pen, I guess. This is base over 3. That distance there. Again, it's from the tall end or the thicker portion of the triangle, base over 3. So whatever the base of that triangle is, the centroid is a third of the way from the tall end of the triangle. Similarly, if you have a rectangle of length L, right, the centroid is going to be right in the middle here. L over 2. It's an L. All right, so take each of these loads and convert them. Let's start with the triangle load. Triangle load. We've got the area of a triangle, 1/2 base times height. So let's write this down. I'm going to put the force here. It's going to be 1/2 the base times the height. So we got a 6-foot base, and the height is 400 pounds per foot. So notice it starts at 0, rises up to 400 pounds per foot. You'll see the units of feet cancel, and you're left with pounds. So 1/2 of 6 is 3. 3 times 400, that's 1,200 pounds. And based on the the location here of the centroid, this acts at So our base is 6 feet. From the left, we're going to have 6 minus 6 over 3. So base over 3. Right? So 6 minus 2, this is 4 feet from the left. Let me sketch this in here a little bit. I'm going to kind of arbitrarily choose a point in here. This is the 1,200 pounds. And I'll label the distance here. This is 4 feet. Right, 6 minus 2 is 4. That's where this comes from. All right, if you look at the triangle, the base of the triangle is 6. Base over 3, that's the distance from this end to the centroid where the force acts through. That's 2 feet. So we've got 6 feet minus 2 feet gives me 4 feet from the left, where this is coming from. All right, let's look at the rectangular load next. We've got the area is just base times height. Right, so that means the force is, let's see, we've got 8-foot base times the height, 400 pounds per foot. Again, feet cancel. You're left with 3,200 pounds. And this is just acting at 4 feet from either direction. So this acts at 8 divided by 2. So 8 is the length. 8 divided by 2 is one end from the right. So we'll put another line in there. Let's see, what do I got? How many lines? 1, 2, 3, 4, 5, 6, 7, 8, 9. So right in the middle, 1, 2, 3, 4, 5. Oh, sorry about there, I guess. Oh, it's in the middle. Let me use my red pen. So this is 3,200 pounds. And let me label the dimensions here. Now, if this is 4 feet, yeah, just do a little math here. The overall length is 8 plus 6, 14. We've got 8 feet already here, so this is going to be another 6 feet. All right, just double check your numbers when you do these conversions. Make sure you're labeling everything correctly, because this is the diagram you're going to use to find the reaction forces. All right, so we've got 6 plus 8 is 14. 6 plus 4 is 10. Plus another 4 is 14. All right, so now we have our free body diagram. This is our complete free body diagram. Notice it has our reaction forces unknown at this point, our applied loads, right, converted from distributed loads, and also important dimensions that we need. All right, so the first thing we need to do is find some of these unknown forces. I think the first thing you can see here is some of the forces in X equals 0. Well, that's just Bx, right? There's only one force in the X direction, and that turns out to be 0. So Bx is 0. That's a pretty straightforward. It's not really a calculation because it's an observation, right? The next thing we do is we say, all right, what do we have to do next? Again, you should be trying to solve this problem before I do. So pause the video and think about what you might do next. And we're left with some of the forces in Y and some of the moments about a point. Yeah, so if you've thought about it, you can recognize that if you do some of the forces in Y, you're going to have 2 unknowns here. And we need to first find one of those. So we can do some of the moments. I chose some of the moments about B. equals 0. Now, you can choose B or A, doesn't matter. If you choose B, you're going to find the force A. If you choose A, you're going to find the force BY. Try it both ways, you should get the same answer, right? This is a good way to practice the problem. So I'm doing some of the moments about B. You try some of the moments about A. Well, either way. All right, so I'm going to look at each force here and figure out what they do. But first, I've got force A, and this is generating, again, about B. This is generating a clockwise moment. So it's a distance of 14 away. So we're going to have negative 14A. And the units on all these are going to be pound feet. I'll put the units out at the end of the formula. And then the 1,200-pound force, again, generating a moment about B. Think about the beam is free to pivot at B. All right, what's that force doing? So A is generating a clockwise moment. 1,200 pounds is generating a counterclockwise moment. So we'll have plus 1,200 times 10 feet. All right, that's the distance it is from B. Put my big brackets here. And then we've got the last term, which is going to be the 3,200 pounds, also generating a counterclockwise moment. So 3,200 pounds times the 4-foot distance. Again, the units on all this are pound feet. Right. Now you can see here that the units for A have to be pounds, right? Because 14 is in feet. You can try to solve this for A. If you do, you're going to wind up with, let's see, 12,000 plus, this turns out to be 12,800. Again, the units up here, pound feet, divided by 14. The 14 is the feet. Well, feet are going to cancel. We're left with pounds. And this turns out to be 1,771 pounds. Now, this came out positive, right? We treated it upwards, positive. So this means this is definitely in the upward direction. And I'll report that at the end in one big box. And then finally, we're left with some of the forces in Y equals 0. So we know what A is, right? A is 1,771 pounds up. BY is unknown. These two are known. Some of the forces in Y is going to give us a lot of information here. So let's see, we've got pointing upward, we have BY, right? And then of course we have pointing downwards. Let's put the AY in here first too. AY was 1771. So we have BY plus 1771. This is pointing up, right? And then pointing down, we have the 1,200 pounds and then the 3,200 pounds. And the units on all this stuff are pounds, right? So let's see, BY is going to be, let's see, we're going to bring BY, well, we'll bring the other stuff to the other side. So we'll have 3,200 plus 1,200 minus 1,771. And this turns out to be, should be 2629. Let me just check. 3,200 plus 1,200 minus 1,771. Yeah, 2629. And this is also positive, right? So it was pointing in the up direction up here. We treated it positive, pointing up, came out positive, so that's also up. So I'll just rewrite my answers down here. BX is obviously 0. BY is 2,629 pounds, pointing upwards. And then A is 1,771 pounds, also pointing upwards. So definitely make sure you're reporting both the value, the units, and the direction for these forces, right? Notice for BX, I don't care if you know, 0 pounds. I mean, 0 pounds is the same as 0 newtons. It's 0 is 0. And there's obviously no direction if there's no force. But these two forces, they have to have a unit and a direction. So make sure you're reporting that. I'm not going to dock you if you report a unit here. I'm just saying, it's not really necessary.